Dear students, welcome back. In the previous lecture, we had talked about the method of isocline and so on. With that, we had completed the first order differential equations. Now, from this lecture, we will move into the higher order differential equations. So, to begin with any kth order differential equation and see some special cases where we can understand and deal the differential equation and then solve the differential equations. Okay, so we have seen all these things in the previous lecture. Now, so henceforth, so from today's lecture, we are going to deal with differential equations which are of higher order. Okay, so in the higher order category, we will do the following techniques. One is that we will introduce the notion of linearly independent solutions, right? This is something very similar to what you must have seen in a linear algebra course, which is linear independent set and so on in a vector space, right? So a similar notion can be generalized to the set of all solutions of differential equations for some special types of differential equations. That will be the topic of today's lecture and probably even the next lecture. And then we will introduce this reduction order technique, okay, which is a technique from where given a solution, from the given solution you can compute a linearly independent solution. Okay, this is a technique to kind of construct or find a linearly independent solution from a known solution. Then we will look at linear homogeneous differential equations with constant coefficients. Then we will look at linear inhomogeneous equations with constant coefficients, and then we will look at linear differential equation with variable coefficients, and then we will look at the method which is the power series solutions. Okay, so this so all these topics will deal with various different types of higher order differential equations. Okay, and some methods are applicable for some special types, and more or less what you see here is that in the higher order case we are only looking at mostly linear differential equations. Okay, most of them are linear differential equations. All these techniques that we are going to introduce is for linear differential equations. Okay, so in this lecture and next lecture we'll probably cover the first two topics. Okay, the rest will be the part of the next lectures, and after this we will introduce this notion of this concept of Laplace transform. After this topic we will introduce finally the notion of Laplace transform. Okay, and with that the course ends. Okay, so these are the topics which we will cover henceforth. Okay, now let's get into today's lecture topic. So recall that so far in the first order situation we have been looking at first order ODEs of the following form, that is, which I said is a very special case, which is it's a first order ODE which is a non-linear ODE where it's linear in the highest order, that is the first order derivative. So it's linear in y prime, the rest of the terms are non-linear. Okay, so now we are going to look at a kth order ODE of similar form, which is the kth derivative is equal to f of all its arguments, which depends on x and y and all derivatives of y up to k minus 1. So there is no yk derivative in this f here. the way you did not have a y prime in this f here, right? So when we say, so here it was linear in y prime, here it is linear in y, kth derivative of y. Okay, so this is, so let's look at this form of ODE, right? So this is a natural generalization of what we have been seeing so far, which is of this form, right? Okay, so now how do we deal an ODE of this form? So the simple way to handle such ODEs is that any ODE of this form, which is of kth order, can be reduced to this form as a first order ODE, but now as a first order system of ODE. Okay, and then we use the same technique which we used for these things. Whenever we could solve this, we could solve here. It's that kind of an argument. So how do we go from kth order to first order system of ODE? So that is the title of this topic. So any kth order can be converted to first order system of ODE. So what you do for that is this. So you look at this ODE here. What all do you have? You have, of course, the independent variable x. Okay, forget that. Okay, you have independent variable x. Then what you have is y, and then the derivative of y up to order k. So you have here, you see, k plus 1 terms. So there are k terms here, and there is the kth derivative here. So 1 term here, so k plus 1 term, right? So these are the unknowns. So you have k plus 1 unknowns, in fact, because y is unknown and all its derivatives are unknown. So you have k plus 1 unknowns. So what the idea is that you introduce, so y is your unknown, so you call y1 as y. So you are introducing, so y is unknown, so you call that unknown as y1, okay, for simplicity now. Then what is y2? You introduce y2 as y prime, and so on. So what I'm saying is that what you have here, this you call as y1, this you call as y2, and then you call the second derivative as y3, and so on, up to what you have here is k minus 1, call that yk. Okay, so you can go on like this. So you call y3 as y double prime, and so on, up to yk as y k minus 1. Okay, so but here you see the reason why we so once we have done this, then yours, as I said here, in fact I should not say k plus 1 unknown, because yk is already given to you from this ODE. So what you actually have is k unknowns. Though you have k plus 1 quantities of y, right? y1 prime, and so on, you have k plus 1 quantities, but yk is already given by this ODE. Okay, so yk is known, so the yk derivative is known via f, as long as you know these things, right? So what you don't know is these k quantities. So if you compute these k quantities here, then you have computed yk prime as well, right? So what is our aim is to compute these y quantities, these k quantities. So that's what we have introduced. So we have k unknowns. Okay, so we have k unknowns, and that's what we have introduced in this what we have said here is that the k unknown, we have introduced k unknowns. So once we introduce k unknowns, we have the system of differential equations, right? Because if y is this, so then yi prime is yi, but yi is by that same definition yi plus 1, right? Because yi is yi minus 1, so y subscript I is the I minus 1 derivative. So the ith derivative of y is yi plus 1. So and this is valid for 1 to k minus 1. So you have k minus 1 equations here already. Via this you have k minus 1 equations. And this one gives you the kth equation. What is the yk derivative? Yk derivative is, right? So here if you notice, from I equal to k here, in this equation, we get yk as yk minus 1. So yk derivative is the kth derivative of y, which is given here, which is f of this, and that's what we have written here, right? So by introducing this k unknowns, we can write this relation. So you have k unknowns and you have k ODEs, k differential equations. So this is a k, so this is a first, and all are first order derivatives. So you started with a kth order differential equation. Now you have first order differential equations, but k differential equations. So it's a system of k first order differential equations, right? So this is how we have converted a kth order ODE to a first order system of ODEs. Okay. So now the advantage of doing this is the following, that now if I let's introduce a capital Y, okay, and I introduce capital Y as this k vector, that is y1, y2 and yk. And you know what are these y1, y2, yk from this equation here, right? y1 is y, y2 is y prime, and so on, right? And yk is yk minus 1, right? So if you introduce this capital Y, then this first order system of ODE here that we have given here becomes capital Y prime is equal to, let's say, capital F of x comma y. Okay, and since this is a k tuple, this f is also a k tuple, so the ith component of f will be defined as yi plus 1 for up to k minus 1, and the kth component will be defined as f of x y1 up to yk minus 1. Okay, so this is your first order system of ODE. So this falls into the category that we have been seeing so far, but of course we did not see a system of ODE. We have seen only a scalar ODE. So here you have k first order system of ODEs. Okay, that's the advantage. So any kth order can be reduced to a first order system of ODEs. Okay, I've written too many here. Anyway, it's so you can see here we started with a kth order ODE. We introduced some unknowns, right? K unknowns, and then we have reduced it to a first order ODEs, but K ODEs, K first order ODEs. And this is what I said. This ODE is, if you introduce the capital Y, it's capital Y equal to f x y. It's in the form that we have been studying so far, except that now it's a system of equations, right? The advantage of this is that the existence and uniqueness results that we have studied for first order ODE can be extended to the first order system of ODEs, right? So the kth order ODE, all questions related to kth order ODE on existence and uniqueness can be reduced to a similar question for first order system of ODE. And first order system of ODE behaves very similar to the first order scalar equation that we have been studying so far, right? So what is the result that we studied about this first order system? The Picard's existence and uniqueness results, right? We did not prove it, but we had talked about it. Similar ideas can be extended to the first order system of ODE. Whatever we did here can be extended to ideas here. So what was the idea here? The idea here was for existence that you have this ODE here, right? You have this ODE, and then you write the ODE, first order ODE, into an integral equation, right? And then you set the solution here, right, is the fixed point of some operator coming from the integral equation, right? That is how we even went into Picard's iteration process and so on, right? All these ideas can be extended here. In any case, we are not going to prove this, and we are not going to deal with first order system of ODE. This is only to tell you and motivate you how to deal a kth order ODE. A kth order ODE of the special form can be reduced to a first order ODE, system of first order ODE of this form. And the techniques that you have seen from, so the Picard's technique can be extended, generalized to this situation as well. Okay, so we will have an existence and uniqueness result for that result. Okay, so that's what we have done. So the Picard's theorem on existence and uniqueness can be extended to first order system of ODEs of this form. Now that's something which we will not do in this course. Okay, we in fact did not even prove the results of Picard's theorem. We did not give the exact detailed proof of the Picard's theorem even in the first order situation for a scalar case, right? So we will not do it, but you should know that it's possible. Okay, so just to compensate for that, we will only state the result for the existence and uniqueness for a linear kth order PDE. Okay, the idea is there. You just convert the linear PDE, this kth order PDE, into the system of first order PDE, and that's how. But the statement, existence and uniqueness statement, is that whenever you have a linear PDE, you recall what was a linear PDE, any ODE which can be written in the form Ly equal to F, where L was summation AKX, right, D so where L is summation K0 to, okay, since I'm using K, let's use I here because I'm using kth order. So AI x di by dxi. Okay, so this is your L, and we said any ODE of this form is a linear ODE, and that's what we have here. Okay, what you have on the left hand side is L of y, what you have on the right hand side is f. Okay, so any kth order linear problem with initial condition, and we have already mentioned that if you have a kth order ODE, you need k conditions. So you have k initial condition, which is all informations about y and the derivatives of y up to order k minus 1. So it's an initial value problem, and this theorem tells you that this kth order initial value problem will admit a unique solution if the coefficients ai and the data f, okay, are all continuous. Okay, and we need to ensure that the leading coefficient, which is ak, that is the coefficient of the y-kth derivative, is not identically 0, because in that case it will no longer be a kth order ODE. It will reduce to the first non-zero coefficient of the highest order derivative, right? So okay, so this is the existence and uniqueness statement for kth order linear ODE. So what is the condition? You just need to assume that the coefficients ai x and the f both are continuous functions. Okay. Now this has a unique solution, right? That's what this this theorem tells you. So the special case when f is 0, that is the right hand side here, f is 0, and the initial conditions yj are also 0, which means the data, both it's 0 here, it's 0 here. In that case, again, as per this theorem, there's a unique solution, and that theorem is the 0 solution. Because you can trivially check that 0, if both f and yj are 0, 0 is, so the constant function 0 will satisfy this initial value problem. And by this theorem, if the solution is unique, then the constant function 0 has to be the only solution. Okay. So now this is something which we have mentioned before. So the advantage of this linear differential equation, right, when we said L, this is Ly, we said Ly is that this L can be seen as a linear map from the vector space of continuous functions to the vector space of continuous functions, which is C of I, which I already mentioned in the initial lectures, right? So when you have a linear ODE, then the linear ODE, then the derivative, so then the linear differential, so the linear derivative can be seen as a linear map from the space of continuous functions to space of continuous functions. Okay, so do it as an exercise, show that the space of all continuous functions is a vector space over R. Okay, you must have already seen these notions in your linear algebra course, so you know what how to check and what to check, right? So this set of all continuous functions has this notion of addition of two functions, right? You can add two continuous functions, it will remain continuous, and so on. Then if you take any, if it's over R, you take any alpha from R, when you look at the scalar multiplication alpha times f, and if f is continuous, alpha times f is also continuous. So all that will show, so verify that this space of all continuous functions is a vector space, right? And when you say this Ly here, when you say your L, this operator which we wrote down as summation ai di by dxi, right? Yeah. Not dxi, sorry, it's d. Here, okay. So so this linear operator can be seen, so this linear operator L here can be seen as a map, okay, can be seen as a map here from the vector space continuous functions. So the vector space of continuous functions to the vector space of continuous functions. Okay, so this is a way of interpreting the linear differential equations. Okay. So once you have the so once you interpret the kth order differential operator L as a linear map, then you have this what is called the notion of null space. So this is something you had even in your linear algebra, right? When you had a linear map or a linear transformation, you had a kernel to that map, you had a null space of that map, right? Similarly, if L is a linear map now from Ci bar to Ci bar, then there is a corresponding kernel to this L, or what is called a null space to L. What is null space? The set of all. So if you take this is your Ci, this is not the right picture, but I'm just writing. So suppose this is your set Ci, you have the same set Ci bar here, and L is a map from Ci to Ci. Okay, ideally for more matured, because we know that this is a vector space and this is a vector space, we usually draw this thing. We usually draw a vector space not as like this, okay, as an R2 kind of set. And this L is a map from Ci to Ci bar. Okay, so don't worry about this. This is just so there is a set Ci, right, and there is a set Ci, and L is a map from the set to itself, right? So what is null space? In this set Ci, there is a zero function. The constant function 0 belongs, because constant function 0 is a continuous function. So if you denote 0 as the function which is constant function 0, then 0 belongs to this set, right? So let's say that 0 is sitting here in the set, something here. Then you look at the inverse image of this 0, right? That will be some set here. And that again, as I said, in the sense of vector space, this is not the right picture. It will be some subset of Ci. Okay. Okay. Let's say this line, whatever I'm drawing here. Okay. Whatever I've highlighted here, this line. This is the inverse image. This is L inverse of 0. Okay, now that is the null space of L. So what is null space of L? The set of all y such that Ly is 0. So set of all y in the domain, okay, such that Ly is 0. That is the null space of, it's basically the inverse image of the 0 element. Okay. Basically all, so what is Ly0? Ly0 is the solutions corresponding to the 0 function. So all solutions corresponding to 0 function form the null space of L. So let's look at, as an example, you can see that d by dx can be seen as a map from space of all continuous functions to continuous function, which will take any element y to its derivative y prime. Okay. Now what is, so if you take 0 in this set, what is the inverse image of 0 under this L? That is all functions y. So what is null space of d by dx? It is all functions y in C, all continuous functions y, such that dy by dx is equal to 0. Now what are those? Precisely the constant functions, right? Because you know from your fundamental theorem of calculus that if dy by dx is equal to 0, then all possible values of y or any constant, right? So what is the null space of d by dx, which is a subset of this domain here, is all constant functions. Right? So all constant functions are the null space of the first order linear ODE. As another example, look at the second order linear ODE. What is the null space of the second order linear ODE? Okay, this means by definition all continuous functions such that d square y dxy is 0. Again, you can use your fundamental theorem of calculus to compute that all functions whose second derivative is 0 is of the form, is all linear functions of this form, right? One degree polynomial in one variable, right? This is the all possible solutions. So this collection for all a and b is the null space of d square by dx square. Okay, so that is the null space of d square. Okay. Now this is a property of the null space. The null space is always a subspace. It's always the subspace of the vector space of continuous functions. Okay, what is the advantage of this? So as we have already said, for instance, the null space of d by dx is all constant functions, right? And how many constant functions are there? As many constant functions as the real number, right? So this set is, so what is the cardinality of this set? This set is as big as the set of all real numbers. So it's a big set, but that doesn't matter in the sense that, for instance, the set of all real numbers is a big set. It's an uncountable set, but it's a vector space of dimension 1. So as a vector, though as a set it's uncountable, as a vector space it's of dimension 1. R is of dimension 1. R2 is again an uncountable set in terms of cardinality. but in terms of vector space dimension, it's dimension 2. Okay, so if your null space becomes a subspace, the set can be very big, but we can talk in terms of dimensions, right? That's an advantage of that. So here this theorem tells you that the null space of this linear operators of this linear ODEs always form a subspace of the space of all continuous functions. So how do we prove this? It's so what should you check for something to be a subspace? If you have from your linear algebra course, you already know that if you take any two elements of the subspace, it should so its linear combination should belong to the subspace, right? And the constant function 0 should belong to the subspace, and so on, right? So you just have to verify these things. So the constant function 0 belongs to the null space. Why? If it's a linear, as we have already seen from the earlier part, that if right, if you're looking for, so null space is defined as all y such that, right, all y such that Ly is 0, and we have already seen what we need to show, that L of 0 is 0. It will be, right, because if we take the constant function 0 and if you apply the linear differential operator to a 0 function, the resulting function will be a 0. So constant function 0 is always in the null space. Now further, if you choose m different functions which are all in the null space, then it's linear combinations. So since they are all in null space, that means that for each ui, Lui is 0 because they are all in null space, right? So then it's linear combination L of this, and use the linearity of f, right? You are going to get, by the linearity of f, you have this, and each of this is 0. Right? Which means this is 0, which means this linear combination belongs to null space of L. So you have shown that if u1, u2, um individually belong to the null space, then its linear combination also belongs to the null space. Okay, so the null space is always a subspace of the space of all continuous functions. Okay, so let's look at some examples to understand whatever we have described. So let's take this second order linear differential equation. So Ly is y double prime plus y. Okay, the second order linear equation. Now you now you observe that both sin x and cos x are in Ly, are in the null space of y. That means L of sin x is 0 and L of cos x is 0, right? For this L, right? Because if you take sin x, then the second derivative of sin is cos is minus sin, so this becomes, so minus sin, plus y is sin itself, so it's 0. Same thing with cos is sin, right? Cos is minus sin, and then minus cos, so minus cos plus cos will be 0. So you can quickly you can observe that, you can verify that both sine and cos, right, the sine and cosine are in the null space of this operator L. And because the null space is a subspace, any linear combination of these two functions will also be in the null space, right? So alpha sin x plus beta cos x for all choice of alpha beta is in the null space of L. Okay. Now as another example, let's look at a third order differential operator which is linear. So this is a linear third order differential operator. Okay. You verify that exponential of x, exponential of minus x, and exponential of 2x, they are all in the null space of this L. Okay, because see y power 3, if you differentiate e power x as many times as you want, it is still e power x. And here you will have minus 2 e power x, here it's minus e power x, and it's 2 e power x. So this is already minus 3 e power x from here, and these two will give you plus 3 e power x. Okay, similarly you can verify for the other functions. So all these three functions are in the null space of L, and since null space is a subspace, any linear combination of these three functions or any two functions, right, should be in the right. So the linear combination of these three functions should be in the null space of X. So alpha e power x, alpha 2 e power minus x, alpha 3 e power minus 2x for all choice of alpha from the real number will be in the null space of L. Sorry, right? So this is the property about null space of this. So in other words, if I know one solution, then I know that, if I know one solution in the null space of, and so null space of a linear operator L, say y, then I know that alpha y are also solutions. If I know two solutions from the null space, then I know that the linear combination of the two solutions is also in the null space, right? So that's so in a sense, I don't have to know. Once I know one solution, since I know all alpha y's are solutions, I have actually spanned over an uncountable collection of solutions just by knowing one solution, right? Okay. So naturally, so the reason of interpreting the differential operator, everything in terms of linear map and vector space, defined on the vector space domains and so on, is that we can use this property of vector spaces in linear algebra, right? So you can introduce this notion of linearly dependent and linearly independent solution. As we have already seen, the linear combination of solutions in null space. So the linear combinations of the functions in the null space are also in the null space, right? So once we have this notion of linear combination and everything, we can also introduce this notion of linear dependence and linear independence of a set of solutions. Okay, so what do we mean by linearly dependent and independent for functions? Now suppose I have a collection of functions, m functions, then we say they are linearly independent. It's the same definition that you already know from your linear algebra, that this collection of m function is linearly independent if whenever the linear combination being 0 implies that all the scalars must be 0. The same definition, right? It's the same definition that you have seen for a linearly independent set, right, in Rn or in the Euclidean space, right? So, and whenever this doesn't happen, whenever the alpha, so even if one of the alphas are non-zero, then you say the collection is linearly dependent. Okay, so linearly dependent and independent set is very similar to what you have already seen for the vectors. In other words, once you view the space of continuous functions as a vector space, then every element, right, every element of this set is now a vector. So any continuous function can be thought of as a vector. But this you should not have, of course, for as for engineers or something, you don't relate it like this. But for us, I mean, at least for mathematicians, the way we view it is that if you have a vector space, and then any element of the vector space can be seen as a vector. Okay, that's how we view it. So in that sense, any continuous function can be seen as vectors. So you have a collection of vectors here, and this is the notion of linearly dependence and linear independence of vectors of continuous functions in this case. Okay, so let's verify them with examples. Now take two functions, x and 2x, right? These are continuous functions, right? So if you take two functions, are they linearly dependent or linearly independent? What should you check? You should check that if alpha x plus 2 alpha 2 alpha 2x, if it's 0, does it necessarily imply that alpha 1 alpha 2 should be 0, right? Now that depends on the domain of the function x and 2x, right? What are the values that x and 2x can take? So let's say if the domain is 0 1, that is x can take 0 and value 1, then if you look at the linear combination and if that is put to 0, then you actually have non-zero alphas for which this can happen, which means it is linearly dependent. So x and 2x are linearly dependent. And that's natural to see, right? You have the function x, and the way you are getting 2x is just by multiplying 2, a scalar. So it's natural that we expect that this is linearly dependent to x, because by multiplying the scalar 2, because the space of continuous functions is a vector space over real numbers, so 2 is a possible scalar multiple, so they are linearly dependent. Okay, now let's look at this example. Take this 3 function, sine x, 3 sine x, and minus sine x. Okay, in this case, whether it's linearly dependent or independent, it's kind of you can naturally see, because from sine x I multiplied 3 to get this, and then I multiplied minus 1 to get this. So we expect that this set has to be linearly dependent, and that is what you will see, that if you take any linear combination to be 0, then you can see that for specific choices of alpha, I mean non-zero choices of alpha, you can actually have this equation satisfied. Okay, so this tells you that this set is also linearly dependent. Now what about these two, x and x square? Okay, so how do I get x square? I take x, I multiply x to get x square, right? This x is coming from, I mean the domain of x is of course real numbers, right? So I am getting x square as some multiple of x, but this x is not a fixed scalar from the vector space field or the vector space over which, I mean the R, right? It is coming from R, but it is varying from R. So what is this set? Is this set linearly dependent or independent? X and x square. So we will show that they are linearly independent. And how do you show that? So we should start with the linear combination alpha 1x alpha 2x equal to 0. Can we find non-zero alpha 1 alpha 2 such that this can happen, right? Now to verify that, what you do, you just differentiate this equation once, So if you differentiate it, you get alpha 2 equal to 0 from if you differentiate here with respect to the x variable. Okay, now in this equation you multiply x both sides. So you multiply x, okay, then you get this equation. So now you have one, you started with this equation 1 here, and then you have one more equation here. Okay, now you solve for alpha 1, alpha 2 from these two equations for all x in the domain. So if you solve for this, you can immediately see that both alpha 1, alpha 2 has to be 0. So if this has to happen, then that can happen only for alpha 1, alpha 2, 0. It cannot happen for non-zero scalars alpha 1, alpha 2, which means that these two sets are linearly independent, right? So basically what is the difference between x and x square is the degree. So a simple way to remember these things is that when the degree is changing, then the set becomes linearly independent. Similarly, as another exercise, you can check what is, take 1 and x. Is this set linearly dependent or linearly independent? As an exercise, you can verify that. Okay, and a quick guess is what is the degree of 1 is 0. The constant function degree is 1 here. So degree of x is 1, degree of 1 is 0. So we expect that this is linearly independent. Please prove it. Okay. So once we have the notion of linear dependence and linear independence, we can introduce the notion of dimension of the subspace, right? Which is something which we already have, right? Dimension. So we have already seen that null space is a subspace, right? Now we can have the notion of which means that we can so null space can have a dimension, and this theorem tells you that for a kth order linear differential operator, linear differential map, the null space is always k dimensional. So that's an interesting result. You see the space of all. So what is the dimension of this? What is the dimension of the space of all continuous functions, right? It is not finite, right? How do you quickly see that? Just in the previous example, I had shown that x and x square are linearly independent, right? In the previous example, I also gave you an exercise, check whether 1 and x are linearly independent, right? Now this 1, x, x square, they are all continuous functions. They are all in this set, right? And these three are linearly independent. Okay. Now x cube is also in this set. In fact, you think of any k, x power k is in this set. Right? So, and they are all linearly independent set. So what do you expect is the dimension of the space of continuous functions, right? It has to be infinity, right? So the reason why this theorem is interesting is because the differential operator is defined on a vector space which is possibly infinite dimensional, right? Whereas the null space is always k dimension. So the null space for a linear operator dimension is same as the order of the differential operator. So if it's a kth order linear differential operator, then the null space is k dimensional. This is something which you have already, which if you have observed in the examples that we have given before, we have already seen this. For instance, when we said when we said the null space of the first order differential operator, what did we show? The null space of this operator is, right, all constant functions, right? It's all constant functions. And what is this differential operator? So the order of the differential operator is 1. Right? So the order of this differential operator is 1. So what is the dimension of this null space? What is the dimension of the set of all constant functions? All constant functions are given, can be spanned by the constant function 1. So you take 1 and you take any real number alpha. So alpha times 1 will give you all real numbers, all constant functions, right? So the set of all constant functions can be generated by just one element, which is 1, or any real number for that matter, right? So a first order differential map had one dimensional null space, which is the set of all constant functions. The another example that we saw was the null space of the second order operator. What did we see this was? This was all functions of the form ax plus b, where a and b can be any real number. And what is this ax plus b? It is if you notice, it is a linear combination of 1 and x. 1, x are linearly independent set, right? And this null space is a linear combination of 1 and x, which are 2 elements. So earlier it was a linear combination of the constant function 1. Now for dimension 2, it's a linear combination of 1 and x, right? So b times 1 plus a times x is what the set null space is for all possible a and b. So it's dimension 2. So the dimension of the second order differential operator is 2, right? That's what we saw earlier. Okay, so this theorem is interesting in the sense that if you have a kth order differential map, then the null space is always k dimension. And you know what the definition of a dimension, right? When you say k dimension, what does it mean? You have k linearly independent solutions in the null space, and which means every other solution of Ly equal to 0 can be expressed as linear combination of k elements, right? That's what dimension means, right? So though null space is very big set, to identify the null space, you only have to find k linearly independent solutions. Once you have found k linearly independent solutions for Ly equal to 0 for a kth order operator, then you have found all the solutions of Ly equal to 0, right? So if you find, so if L is a kth order differential, so if your L is L is this operator starting from 0 to k, so L is kth order, and if you find y1 such that Ly1 is 0, if you find y2 such that Ly2, if you find y2 such that Ly2 is 0, and so on, if you find k solutions such that this set y1, y2, yk, if this is linearly independent, then that's enough. You have found, if you find k solutions which are linearly independent to this equation, then you have found every other solution, because every other solution will be of the form alpha 1 y1 alpha 2 y2 plus alpha k yk. And this is what we have been seeing so far as the notion of general solutions, right? So any solution will be of this form as a linear combination of this k linearly independent solutions. So that's the advantage of this theorem. Okay, so let's and that's what I mentioned here. So the general solution of a kth order linear homogeneous ODE. Homogeneous means the f is 0 here because we are looking at null spaces here. Okay, so the general solution of the kth linear homogeneous ODE is the linear combination of k linearly independent solutions of ODE, right? So because the dimension is k for a kth order operator, it's enough to find k linearly independent solutions. Let's look at some examples, something which we have already seen. We have already seen the second order differential operator. So as per the previous theorem, the null space of this operator, because it's second order, the null space should be 2 dimensions. Okay, we have already checked that sin x and cos x or solutions are in the null space of L, of this L, right? Show that sine and cos are linear, sine and cosine are linearly independent. So we have found 2 solutions, sine and cosine, and they are linearly independent solution. Because it's a second order linear differential operator, the null space should be of 2 dimension. So every other solution of this second order ODE should be linear combination of sine and cos. Okay, that's an obvious consequence from the previous theorem. Similarly, let's take whatever the other example that we have seen earlier is this third order differential equation. We have already verified that e power x, e power minus 2x, e power minus x and e power 2x are solutions, are in the null space of this L. Right? These 3 functions are in the null space of L. Please verify as an exercise that these 3 are linearly independent solutions. This is a linear operator of, or this is a linear operator, linear differential equation of order 3. So the null space should be 3 dimension. We have found 3 linearly independent solution. That means every other solution should be a linear combination of these 3 solutions. Okay, so these are the ideas, advantages of viewing the differential operator as a map from vector space to vector space and seeing the null space as a subspace and so on. Okay, and these are called, so this is the general solution of the differential operator. So the linear combination of linearly independent solutions is the general solution, which means every other solution can be obtained from specific choices of alpha, beta. Right? If you choose specific some special choices of alphas, then you get special solution. The kind of particulars. Each solution can be obtained for each choice of alphas here. Okay. Okay. So with this, we have introduced the notion of linear independence and so on. The next lecture, we will continue again from linear independence, give other equivalent how to verify the linear independence of solutions and so on via Wronskian and so on. Okay, so see you in the next lecture. Thanks a lot. Bye.